What do we need to implement TinyProlog? Well, we will need the same things as in the previous tasks. We will be using algebraic data types to represent Prolog programs, and we will be using unification that we have written already, and we will wrap this together in a couple of recursive functions. But there's one more thing that can help us with some of the more advanced problems in F#, and that's active patterns. So in F#, we've been using match to do pattern matching on our programs, and typically we've used match with the predefined cases of an algebraic data type or with lists. But active patterns is a feature in F# that lets you extend this pattern language. So you can define your own pattern like odd or even and use those to pattern match on numbers. You can do this, use this to recognize some special particular forms of terms, and as you will see shortly, there are two different kinds of active patterns. The other thing that we will need in this lab is to write some code that generates a sequence of items. This is something that exists in a couple of other languages. There's comprehensions in Haskell or generators in JS, JavaScript, where you have some code that can yield or produce multiple values that are then collected in some sort of collection. In F#, you can collect the data in a lazily generated sequence. This corresponds to IEnumerable in .NET, or you can create a list using the F# linked list, or even an array, which is the syntax with square brackets and a pipe. So let me show you a couple of advanced things. The first one is the odd and even active pattern. So let's say we want to write code that will write tick for odd patterns, for odd numbers, talk for even numbers. The syntax for defining an active pattern is, again, we are using let, but rather than putting a function name here, we use this special funny banana bracket syntax where you open it and then you list all the different cases that you can recognize and then you close it. So if the n is divisible by 2, then we are going to return even, otherwise we're going to return odd. And the nice thing now is that I can use this in a pattern matching construct using match. So I can pattern match a number n against odd, and then I'm going to print tick. And if it's even, I am going to print talk. An interesting thing here is that F# can still check your pattern matching for completeness, because this syntax odd even is saying this is a complete pattern and any number is either odd or even. So if we run this, then we get a couple of TikToks, and this was an example of a complete pattern that categorizes numbers into two classes. But I can also write an incomplete pattern that will sometimes say, yes, this number is a square of two other numbers, but sometimes it will say it's not. So how do we check if a number is a square? Well, I'm not going to do anything very clever here. I will just say convert the number to a float, take a square root, and then convert the result back to int. And if this was indeed a square root, then I'm going to return sum, and otherwise I'm going to return none. So for these partial patterns, you have to return an option. Either you're matching or you're not. And if we now define this again, then we can detect squares and print what square is it. And if we run this, then run it again, we get 1 squared is 1, 2 squared is 4, 3 squared is 9. So this seems to work. A little more interesting example that we can implement is that you can actually use these active patterns recursively as well. So let's say that we have a list and we want to check if all the items in the list are some squares. So I can match the list with the usual pattern. Well, if it's an empty list, then indeed everything there is a square. So we're going to return sum of an empty list. But what if it's a cons cell? Well, if this is some list, then it is all squares if the tail is all squares. So this is one part. And also the first element is a square. And if that's the case, then we're going to return some x and x's with the numbers that are squared here. And if it is some other thing, then it doesn't contain only squares and we just return none. So I can now pattern match a list that contains some squares with squares and print all squares. And here's my list that we get. And otherwise, I'm just going to print not squares. If we run this, then we get not squares because I made a silly mistake and I included 2 in my list. So if we remove 2, then it does actually print all squares, and it's square of 1, 2, 3, and 4. So this is a useful trick that you may need in one of the more advanced exercises. Now the other thing that I wanted to show you is one case where this is actually useful. So I have a little definition of an expression which can be a constant or a binary or a unary. You've seen things like this in ML or in BASIC. So I have a little expression that represents -3 times 2. The whole thing is then minused and subtracted from -4, or added to -4. The point of this is that one operation that we may want to now implement is extract all the constants from this. So what if we want to extract all the constants here from an expression? Well, if the expression is a constant, then this is easy, and we are just going to return a list with n. But now we would have to write 2 cases to cover the binary operation and the unary operation. And in this case, this wouldn't be such a big problem, but it's a little bit annoying because you have to write 2 cases. And so what we can do to make this easier is that we can define an active pattern called operation that will match both binary operations and unary operations. And if the operation, and it will return the children or the sub-expressions of these expressions. So if it is a binary, we return a list with E1, E2. If this is unary, then we return the list with E. And otherwise, we return none because this is not an operation. And so now if I define all of this, I can say if I have any operation with some e's, then I'm going to collect all the constants inside ES. The collect operation iterates over all the elements in ES. for each of them, it calls the constants operation recursively and then collects the results. And so if we say constants of E, then we do get back all the numerical constants inside E. So this is a clever trick that can help you if you want to write pattern matching on terms that, for example, in this case, can contain different sub-expressions in different cases. This is also one of the cases where F# actually cannot quite detect that we are covering all the cases. Because in this case, we are indeed covering all the cases. Operation is covering all the binary and unary cases, and constant is covering the third remaining case. But F# cannot analyze the insides of the operation, and so it doesn't know that. All right, the other thing that I wanted to show you is the sequence expressions in F#. So the simplest thing we can do here is generate numbers from 1 to 10 and generate squares. And the way you do this is that you can write a for loop inside these square brackets to create a list. And then we say for every number in 1 to 10, we're going to produce a square. If we do that, we get a nice list of squares. And you can turn this into an array using this syntax, or we can create a sequence expression, and this is going to be a lazily computed list using this syntax. You can see here that there's ... because the F# interactive doesn't know how long the list will be. The syntax with this arrow is a shorthand for something that's a bit longer, and you can expand this and write things like this, where we say for all numbers, do some computation that will yield the square. And this now starts looking much more like ordinary F# code, and indeed inside here you can do things like write pattern matching. So I could, for example, instead of generating squares, I could iterate over all the numbers and only yield squares. If it's not a square, then I'm going to write unit. This means don't do anything. And this gives me a list of if I was actually yielding the squares, or maybe a tuple with the number and its square, then I get something like this. So this is an interesting example, and you can do more things with these sequence expressions. And one interesting thing is that you can define them recursively as well. So I can define a recursive function called squares that takes a number, and what it's going to do is that it's going to yield the square of this number, and then it's going to recursively call itself with n+1 to yield all the remaining squares. And this is a function that does actually produce an infinite or potentially infinite collection, and you can still do operations on this. Another way of defining the same thing would be to just generate numbers. So here I'm going to yield the number itself, and nums will give me just a sequence of numbers, and you can still use operations for processing collections like seek.map, which for any number I'm going to take the square, and now again I have a list of squares. So that was all F# that you will need in TinyProlog, and let's have a look at the code structure of TinyProlog. Again, we are using a nice F# algebraic data type to represent our terms. So a term can be either an atom, variable, or a predicate. And in one of the more advanced examples, we will also add support for calls, but that's a bonus feature. So the important distinction here is that there's an atom and a variable. Those are both some named things, but atom represents a single item, single element that exists in our closed world, and variable is a placeholder that we will be assigning to in unification. Predicate then has a string, the first string, that's the name of the predicate, and that's followed by a term list. And the sort of special thing with the call is that this is calling a predicate that's defined by a term rather than a string. And our program will be then a list of clauses, and a clause can be either a fact, in which case it just has a head and an empty body, or it can be a rule, and then it has both a head and some term, and some body, which is again a collection of terms. So to create a fact, we create a clause with head and no body. To create a rule, we're going to create a clause with head and a body. The unification process will work in a very similar way as our type inference. And here in TinyProlog, we split it into two functions. Unify, that looks at a term, and unify lists, which will then look at and sort of try to match, for example, the arguments of a predicate. And when we do unification, we will again generate a substitution or an assignment for variables. In TinyProlog, we will have the same two uses of substitution in this key operation that then has to substitute in all the remaining unprocessed goals, and after doing the recursion, it has to apply the substitution to the result. Important fact is that we will need to rename variables when using rules from the program database, because each time we apply the rule, we're using a new instantiation of this universally quantified variables. So the core operation of unify and unify list is split into two functions here to make this a little bit more readable. And unify list goes over two lists. If they're empty, then that's an empty substitution. If both of the lists are non-empty, then it tries to unify their heads. And if this works, we get a substitution, and then we have to continue recursively on the tails. If one of the lists has different length, then that's a failure. And the unification, the core operation, similar to what we did in TinyML. So we will be if we match two atoms, then they match only if they're the same. If we have a variable and something, then we generate a new record in the substitution. And the interesting case is that we now have these predicates which have variable number of arguments, and so we can unify those using unify lists, but only if the names of the predicates match. Later on, we will want to do a little bit of Prolog programming with numbers and lists, and you don't actually need anything extra to do this, because we can represent numbers using the piano arithmetic, and we can embed lists into TinyProlog using predicates. So a 0 will just be an atom, and number 1 will be the successor of 0 represented using a predicate S. An empty list is going to be an atom empty, and a list with some element will be a predicate with one argument, the item, and at the tail, rest of the list. This is good enough for our Tiny implementation. It is terribly inefficient, and it will also generate an extremely ugly terms. So this is why I talked about active patterns, because when we print Prolog terms, we will want to do this in a nicer way and print number 5 rather than SSSSS0. So what are the steps here? The first step is to implement unification of terms. So this is something that will hopefully be familiar. We will be recursively matching the atoms against atoms, variables, and predicates. Once we have this, we will need to be a bit more careful about composing substitutions, because we might, when we do the SLD resolution, we will be doing more operations on substitutions than we did, for example, in TinyML. So we will have some more infrastructure for working with substitutions. In step 3, we will implement this searching operation that looks through all the rules in our program database, finds the applicable rules, and tries to unify the head to get a substitution. And in doing this, we will also need to implement variable renaming. Once we have that, we will do the key bit, which is to implement the SLD resolution, which generates a list of goals, picks the first goal, tries to find an applicable rule, updates the substitution, and does this recursively in the loop. And once we have done this, we will add numbers to our TinyProlog, or really they will already work, but we will add a couple of functions for working with them in a nicer way. If you want to do more, we will change this, the implementation, to not give us all the solutions immediately, but do this lazily, so that we can ask for more solutions, and we will extend our pretty printer to work with lists. And once we have done that, you will actually be able to run the magic squares operation in TinyProlog. And this, by the way, will show how slow our implementation is. For much more sort of interesting and complicated problems, we can add this call operation, which lets us define a functional map operation on lists. So call is an operation that lets you do something like lambda functions, where you can say, I want to call a specific thing that the user gives me on a given input. So like calling a function that was given to you as an argument, and as additional bonus tasks, you can try to implement occurs checks and see if that makes the program slower. And we can also implement, if you want to do real programming in Prolog, there's the cut operation, which is a special trick to deal with negation. So you can try to implement that as well. So why is TinyProlog an interesting programming system to look at? Well, the interesting thing here is that its evaluation is very different from anything that we've seen elsewhere, because the evaluation works as a search operation rather than some sort of reduction in a sequence of steps. And the core of TinyProlog is remarkably similar to ML type inference, and that's not a coincidence, because it's based on the same unification, and also Prolog, and that operation of Prolog, as I was saying earlier, is the basis for various other systems that do derivation or solve some constraints, and that's exactly what ML is doing. But of course, TinyProlog, again, is a tiny system, and you would need to do much more to make it actually practically useful.